again. Fancy seeing you here. Uh, let's go for it. Let's finish up Unit 2. Um, again, this is one of those, we're going through this unit fast because it'll come up a lot. We'll get a lot of practice and it will build us more time later. So if you feel like this is going a little fast, especially because I'm doing these notes via video, I get you. Um, we'll take care of it. Uh, you'll be fine with this eventually. Okay, so let's talk bivariate data. We're still in Unit 2. Now we're representing the relationship between two quantitative variables. So last class we looked at two categorical variables. Now we're looking at two quantitative variables. And so bivariate data, I'm going to try typing some of this because I feel like that's nicer for you in some respects. Let me see if this works. Okay, so bivariate data is data on each of two quantitative variables where each value of one variable is paired with a value of the other variable. Okay, so not the most exciting. Oh no, I don't want to highlight there. I want to. Interesting. Learning new things. I see. I want to make that. Okay, now you're just getting to watch me fuss with the typing, which is probably not what you're here for. Although, teachers, they're just like us. All right, let's move this down and call it a day. All right, bivariate data. So basically, you've been dealing with this for a long time. Back to writing. You've got explanatory variables and response variables. So explanatory variables are sometimes what you would call independent variables. You could also think about this as your X variables or your inputs. You also have response variables. So this is what we tend to think of as our dependent variables, although in stats we want to call them response variables because we can't always know that it's an associated relationship. So we call them response variables. And you could also think about this as your Y values or your outputs. Okay. So take a second. If we think about a baby growing, right? A baby is born, it starts growing. So we could think about the baby's age in months and the babies are measured as length, not height, because they don't stand immediately. Um, so baby length. And we're going to say in inches because America. Okay. So take a second for yourself. Which one of those would be the explanatory variable and which one would be the response? And so again, explanatory kind of has that word explain in it. Which of these two things likely explains the changes in the other? Cool. So the age in months, we would probably think about as our explanatory variable. As the baby gets older, it's probably also increasing its length. We probably have a positive relationship there. It's unlikely that the baby's increasing length is causing it to age, right? So if you're not sure which should be the response variable or the explanatory variable, try it both ways. Sometimes it's still a little murky. often it's very, very silly in one direction. Like if you want to stop aging, just stop growing. No, we can't do that. All right, good. So explanatory response variables. Now, this is all harking back to scatter plots. And so scatter plots, you may have even encountered in Math 1 or Math 3. So that's why we're thinking about our X's and Y's. When we're describing scatter plots, just like before, we have some components that must be covered when we're describing a scatter plot to completely describe a scatter plot. First up, always use context, right? We're always BSing in this class, being specific. Then the three things to consider are we've got our strength. And so our options for strength are weak, moderate, or strong. You always want to mention the strength. Then we also have direction. And what we mean by this is largely the slope. So is it positive or negative? Strangely enough, for AP stats, we really just focus on linear relationships. So a lot of different types of relationships won't have a constant slope per se, but there could still be a very strong relationship. We're not really that interested in those for AP stats, but they're super interesting for actual real world modeling. And so that takes us to our third component, strength, direction, and then form. For our purposes, form is either linear or nonlinear. Like I was saying, this is really all we're interested in for AP stats. There's some cool stuff with nonlinear modeling and nonlinear regression. It requires a much greater depth of statistical knowledge and of, frankly, computer programming knowledge. So that's too much for an intro course. But if you like this stuff, if you're interested in like prediction, finance, I think econ does some of this. Nonlinear modeling is fascinating. All right, so what might that look like, right? Why did we have this big space? Well, I'll tell you why we have that big space. We're going to draw some pictures. Yay. All right, so I'm going to draw 3 scatter plots. And you do not have to perfectly mirror my scatter plots, but get the gist. Okay. So take a second, pause this video. I want you to describe the strength, direction, and form for each of these 3 scatter plots. And maybe this one should be a little more like that. Okay, hopefully you did that. I'm going to move forward. So our first one over here, I would say that there's a pretty clear pattern here, but it's not super, super tight. So I'm going to call this a moderate relationship. The slope, as we move from left to right, as the x's go up, the y's are going up. So the slope here is going to be positive, or the direction is going to be positive. And then see a place where a line could go. And so we're going to call that linear. It's linear enough. Okay. So moderately strong, positive linear relationship between whatever the x value is and whatever the y value is. Next, this guy. So hopefully you can see that little bit of curve. I would say this is moderate to strong in terms of how tight the pattern is. So I'm going to say that moderate to strong. Don't worry too much about being able to tell perfectly, oh, is this a moderately strong or a strong relationship? You'll know it when you see it. And you'll get a lot of practice. I've got some delta math problems to help you practice, like when is it strong, when is it weak. It's not something you need to have like perfect thresholds for. It appears that as the x's get bigger, the y's get smaller. So this one is going to have a negative relationship, a negative direction. And because of this curve, I'm going to call this nonlinear. There's a line of best fit that goes through here. But when we look at something called the residuals, the distance between the actual values and the predicted values from the line of best fit, these residuals are going to give us a curve here. And so that's going to accentuate the fact that this is a nonlinear relationship. Finally, last but not least, who knows what's going on here? I would call that very weak, if anything. I don't even know if we're like entering the gym here, much less lifting a barbell. There's no clear direction, right? It makes just as much sense for me to draw that line as it does for me to draw that line. Like, what's the difference there? And then in terms of the form, is there any form? This is what we would say is something with no association. Wow, I can spell. Okay, no association. This would be something like GPA of a senior and height, right? Like year of car manufacture and something else completely unrelated. Like there's lots of spurious correlations, right? Things that seem to be correlated or seem to be strongly correlated, but really aren't. But this, it's just nothing. No association. Doesn't look like anything to me. All right. So there we go. Describing a scatter plot. Onward. These are long notes. I'm sorry. I'm going to try to yap less. So correlation. Correlation measures the direction, and strength of linear relationships. Only of our linear relationships between two quantitative variables. So I meant to get rid of this word meaning. Basically, we have this letter. It's a lowercase r. That's the correlation coefficient. Okay. Now, the correlation coefficient is not the slope. Be very careful about that. It's always with regards to a linear association. And the correlation is always from -1 to +1. If the correlation coefficient R is -1, this is a perfect line. You are almost never going to get this in real world data, but this would be a perfect line with a negative slope. It's not that the slope is necessarily 1, but because the correlation coefficient is negative, the slope is negative. It could be a perfect slope of -10. Could be a perfect slope of -1.3. It's just negative and it's perfect. Conversely, if it's a +1, this is a perfect line with a positive slope. Now, this is definitely worth taking note of. The closer R is to -1 or 1, aka the farther from 0 in either direction, the stronger the association. So a correlation of coefficient of 0.8 is going to show a much neater line of data, not perfect, but neater than a correlation of 0.4. I think I said 0.8, right? So closer to 1, closer to -1, stronger line. Closer you are to 0, the fuzzier it gets. This correlation right here is going to be pretty much 0. This is probably going to be like 0.6. I'm making that up. But, right, it's not that close to 1, but it's more than halfway there. This one would probably have like a negative, maybe even a -0.6, but we've got some other stuff going on there that makes us know this isn't linear. Okay. So, for the interpretation, it's very, very important to note, and you've heard me say this, and I will say it again. Correlation is not causation. Maybe I'll include a link to some of the spurious correlations, but they're very funny. It's like the popularity of the name Elizabeth and the per capita consumption of cheese very strongly correlated, like totally clearly unrelated, but the correlation could be very strong. So it's a fun little website. All right. Good. In terms of our calculation, I want to show you how we get this, but I don't really ever want you to do this by hand. So this is one of those, it's interesting to see where it comes from, but we don't want to think about using this on a regular basis. So the correlation coefficient is calculated by taking 1 over n minus 1. So we're dividing by 1 less than the sample size. The sum of the distances of each x value from the x's over the standard deviation of the x's times the y value minus the average of the y's, the difference between those, over the standard deviation of the y's. That's a lot. Again, don't worry about this one. It's good to know. We don't have to use it. All right, onward. Linear regression. Then I'll take a pause. So A linear regression model is extremely similar to y equals mx plus b. However, because we're going to be fussy, in AP Stats, we use y hat, I'm going to label this, is equal to a plus bx. This is super annoying because we've been hounding you about y equals mx plus b, and now b all of a sudden is our slope. A is our y-intercept. Y hat, and so we pronounce that y hat. We're going to have a few different hats in this. The hat means that it's a predicted value. The y hat is a predicted output. So based on our regression line and a given input, y hat is our predicted output. You could also write this as whatever the response variable is, with a hat. So like baby length hat is equal to a plus b times the explanatory variable. Buddy, don't yell. Can you hear my cat yelling? He loves this. Okay, great. If you're going to use X and Y, you have to define them, right? If you're going to use a variable, you have to define it. If you don't want to define the variables, just write them out, right? The predicted baby length is A plus B times the baby age in months. Easy peasy. Okay. So last little bit on linear regression here. Extrapolation. So the definition for this is using a linear regression model, or really any regression model, but we're sticking to linear in AP Stats, to predict for, I'm going to go back. I'm going to say to predict outputs for explanatory variables, aka our x's, outside the data set from which the model was built. So what does that actually look like? If we think about a little graph here, right? And let's say we have a bunch of data here, right? It's all in a line. It's reasonable to say, okay, here's my line of best fit. Maybe it's like this, right? Some line of best fit through there. It would be reasonable to say, hey, I've got another data point right here. Based on my model, I think based on my X value, my Y value is going to be about here. That's reasonable. That's within the bounds of our data. Extrapolation would be, okay, I built a model based on data here. Now I have an X value way over here. And so I'm going to use it and I'm going to follow this line of best fit. And I'm going to say that this pattern that I found over here continues forever and must be true and is a valid predictor for an X value way out here. Right? We don't know that. Think back to our babies right? The baby age and the baby length. Thankfully, none of us continued growing at the rate that we did when we were babies. We would all be monsters and we'd have to do basically nothing but eat all the time to sustain life as a creature that large, right? So we can't use a model that was built on babies aged 0 to 18 months to predict height for someone who's 180 months. That wouldn't be reasonable. The patterns that you see from 0 to 18 months in human growth don't continue indefinitely. So, extrapolation, sometimes it's okay, right? If we had a model for babies age 0 to 18 months and we used it to predict the length of a baby who's 19 months, that's not crazy, right? It's still technically it's extrapolation, but that's not crazy. But again, using it to predict the height for a 10-year-old or a 20-year-old, that's crazy. That's assuming way too much beyond what we actually have data on. So keep that in mind. I'm gonna see. Can I pause this and come back to a recording? Let's see. Pause. I found another cat. Maybe. So many cats. Okay. Great. Welcome back. Now, least squares regression lines, LSRLs. Again, maybe you talked about this in Math 1. Maybe you didn't. Let's review. An LSRL is a least squares regression line. LSRL. Mystery solved. This is a line such that each data point has the minimum, nope, that's not how you spell, minimum distance possible from the overall I dropped a word there, huh? Oh, I can't spell possible either. So that each data point has the minimum distance possible from sort of the overall group of data. This is also known as the line of best fit. Now, we're going to do this in the calculator. No reason to do this by hand, certainly not more than once. So in the calculator, the slope is b. And to calculate b, if you wanted to, you're going to take the correlation coefficient and multiply that by, instead of the change in y, it's the standard deviations of y over the standard deviations of x's. So just like in slope, y over x, there we go. We're going to go through with found an online emulator. We'll go through entering some data and calculating the LSRL. But please do this in your calculator and learn how to read the output. Don't worry about calculating this by hand. So the slope and y-intercept in context. All right. For the slope, I'm going to try and type this one. I really think it'll be better. I'm going to try again. Not the definition of insanity to do the same thing and hope for a different result. Okay. So there we go. Oh, I really just want to know how to change the text color. Anyway, the slope and y-intercept in context. So for the slope, I want you to use this sentence stem. Exactly this sentence stem. Don't get fancy. For each additional, and then insert your x variable unit. So for each additional a age in months, right? Each additional month. The insert y variable unit. The baby length is predicted to, and then it's increase if the slope is positive, it's decrease if the slope is negative, by approximately, this is another one, you have to make this an approximately. Whatever the slope is, and then you're going to use whatever the y, the international x unit, the y is predicted to increase or decrease by approximately blank. Yeah. Y variable units. Okay. Every single time, this is how I want you to interpret the slope. Every single time, write it this way. So I'm putting it in quotes. There's many, many things in AP Stats that you have a lot of freedom and ways to be creative. This is not one of them because it's so, so easy to say something that sounds okay, but is not quite right. Similarly, the y-intercept, this one's a little more sensical. I'm not putting it in quotes because you can be a little more free with it. The y-intercept interpretation is just when x is equal to 0, right? When the baby is 0 months old, the predicted y is whatever the intercept is. And then for this one, decide if makes sense, right? So babies are absolutely born with some length, right? It makes sense to have a y-intercept that's some positive number of inches. But maybe you're modeling something, about like baseball attendance or something with data way far out. Well, uh maybe it's like a number of games won per season, right? On a baseball team. I don't know if there's been a professional baseball team that has won 0 games, and maybe that would make sense in context, but maybe you're also going to end up with like a negative number of spectators. So you want to think about, in the context of this situation, does it make sense for the x to equal 0? And does it make sense for the y to equal 0? If either one of those is a no, then the y-intercept does not make sense in the context. That's okay. It's still there. It's just not contextually sensible. Okay, onward. R squared, coefficient of determination. This is also something that I want you to interpret very robotically. So the coefficient of determination is the percent of the variability in y that can be explained, or that is accounted for, by the variation in x. Okay, so I'm going to put that in quotes because I want you to say it the same way every time. And again, thinking about our babies. We know that there's a lot of genetic factors that affect how tall a baby is at any given age, right? I was fairly tall, long for my age as a baby because I was just growing really fast at the beginning and then I stopped. Some of you may have been small um, for your age. Some of you were like right on that 50th percentile. All good things. You're all great. But we know that at some point we were all 6 months old. And us being 6 months old had some contributed some to how big we were. But other things also contributed to how big we were when we were 6 months old. And so maybe, 40% of the variability in 40% of the variability in baby length can be accounted for by the variation in baby age, right? But there's lots of other factors besides just age that contribute to how long a baby is, how tall a baby is. So, this is one you're probably going to have to just grapple with a little bit for a little bit. But for now, if you're asked to interpret R squared in context, this is the sentence stem to use. Okay. Onward. Residuals. Wow, this is an action-packed day. I hope I'm back at school for this. I hope I've made this video for naught. All right. A residual. What a residual is the distance between the actual value and the predicted value. How you do that, how you calculate that is your actual value minus your predicted value. That equals your error. Yay, introducing all sorts of letters that we use in other ways. So, again, this is actual. This is predicted. You'll notice this is a common theme in statistics. It's actual minus predicted. It's actual minus mean. It's observed minus expected. It's always what you actually got, your actual data point, minus what you're expecting. That is a common theme in many, many of our formulas. And then that E stands for residual. For residual plots, there's really just one big thing. The key thing here is you do not want to see a pattern. If there is a pattern in the residuals, if there is a pattern in the residuals, a linear model is not appropriate. This is something that will come up frequently. If this concept is getting assessed, this is how it's going to get assessed. You're going to be given a scatter plot and or a residual plot, and especially a residual plot. You look at those residuals. If there's a pattern, not appropriate. Okay. So, almost there. You're doing a great job. Look, we're almost done. And we're going to go super quick on this. Basically, when we're looking at outliers in regression, a high leverage point, these are both types of outliers. This is one that is far from the other data, and it makes the correlation appear stronger. So what that might look like is if we have our scatter plot and pretty much all of our data is like here, and it's like okay, there's some sort of pattern. But then we have this high leverage point way out here. That's going to affect in the calculations of our LSRL. This data point is going to have an outsized effect that makes this appear much stronger, even though most of the data here is moderate. An influential point is another type of outlier, and this is one where the X value is in the mix. And so what I mean by that is it has similar values to the other X values, but the Y value is very different. And this has a disproportionate effect on the slope. It's a thing, so we're going to use effect. A for action, A is the verb, E is the noun. Disproportionate effect on the slope. I think I used the wrong effect last year. Okay. So what that might look like is we have a bunch of data, but then we have this one wacky point down here. So normally the slope's going to be like that. But because of this data point, we're going to get a slope that gets pulled much steeper in this case by that data point. It could be much shallower, like whatever it is. This is disallowing our line of best fit from really mapping pretty much all the data. Now, these outliers, they might be errors, they might not be. You can't just throw them out because they don't fit what you want, but you should investigate them and figure out what's going on. Okay, for transformations of variables, last bit here. Sometimes you'll see sometimes you'll see roots or logs of y hat of the predicted value. Just do normal algebra to isolate y hat if you want the predicted value. Frankly, this is content that they are de-emphasizing or eliminating when they revamp the course and exam description for not this school year, but the following school year. And when the College Board decides it's not going to be on the next version of the test, the College Board stops spending time and money writing questions on that content. So you might see it. I'll throw one or two your way just to make sure we're ready for it. Not a huge deal. Okay. I'm going to stop there. I'm going to make a second video that's just walking through a couple calculator things, but I think we'll all be better off if I pause this one here. We can do some cat tax real quick, though. That I think is worth it. Love me your cat. Cat. Oh, this is baby. She is a little camera shy and doesn't like being woken up from naps. I'm so mad. Okay. All right, buddy.